This lecture is about substitution in lambda calculus. So last time we learned the syntax of lambda calculus, where we have two syntactic categories, expressions, which defined as variable, lambda abstraction, or application. And we have another syntactic category called value, which consists of these lambda abstractions. That's the syntax. And we also formulated the operational semantics based on this notion of reduction. E reduces E prime. This is called E reduces to E prime. So if you have this relation, then we take this value V as the meaning of this expression. In this way, operational semantics explains the meaning of every expression in lambda calculus. And with this reduction judgment, we formulated the operation semantics with either call by name reduction strategy or call by value reduction strategy. So in the case of a call by name reduction strategy, we have two reduction rules. First, if you have expression E1 applied to E2, you first try to reduce the first expression. So expression E1 reduced to E1 prime, and you reduce the whole expression into E1 prime, E2. So this is the first reduction rule in this operation semantics under call by name reduction strategy. And there's another reduction rule, which is if you have a lambda abstraction applied to another expression E prime, we have this substitution operation. E prime substituted for variable x inside expression E. So this is the reduction rule, application reduction rule. And the idea behind this substitution operation is actually simple. Informally, we'd like to substitute expression E prime for every instance of variable x inside expression E. That's the informal description of this substitution operation. But in the previous lecture, we did not give the formal definition of this substitution operation. And in the lecture today, we are going to formally define this substitution operation in order to complete the definition of this operation semantics. So the remaining job in formulating the operation semantics for lambda calculus is to give a precise definition of this substitution operation, which is the topic for the lecture today. So in order to define this substitution operation, we will need several new notions. First, free variables as opposed to bound variables. And we also learn the notion of closed expression. A closed expression is basically an expression with no free variables. And we will also learn an equivalence relation called alpha equivalence relation, which we write as E equivalence alpha E prime. Or you can think of it as, you can also call it alpha conversion. And we will also use a new operation called swapping. X bidirectional arrow Y expression E. And finally, we will give a formal definition of this substitution. So the informal description of this substitution is actually easy, but it turns out that the formal definition of the substitution is quite tricky. You need all these notions in order to formally define substitution. Therefore, formally define the operation semantics. So these are these are new concepts that we will discuss in the lecture. So let's first talk about these free variables. So free variables are basically variables that are not bound variables. So in other words, if a variable x, it is either bound in a lambda abstraction or it is free. So the working definition of a free variables is a variable is free if it is not bound, if you cannot find a corresponding this lambda binder. So for example, in this case, this variable x is bound to this lambda binder. So this is a bound variable. And if you cannot find such a corresponding lambda binder, then this is going to be free. So here's an example, lambda x, xy. Recall that the scope of this body of a lambda expression extends as far to the right as possible. So you can imagine that there are parentheses omitted here. So this variable is bound because there you can find the corresponding lambda binder here. On the other hand, this variable y is free because it has no such corresponding binder. So that's the idea. That's the notion of free variables as opposed to bound variables. And we can formally define a function that calculates the set of free variables. So let's introduce a new function, fv. So let's introduce a new function called fv that stands for free variables. So this function is going to calculate the set of free variables in expression E. So because we define this expression, the set of expressions inductively, we are going to define this function as a recursive function. So there are three cases. Expressions are either variable, lambda abstraction, and application. So this is inductive definition. Similarly, we are going to define this function free variable function as a recursive function. So first the case is this case. What is the set of free variables in this expression? This variable x has no corresponding lambda binder, so it is counted as free variable. The next case deals with this lambda abstraction. So free variable, lambda abstraction, E. Here, we first calculated the set of free variables in the expression E. And then we are going to remove a variable x from the set because if x is indeed a free variable in the expression E, it is going to be bound here. So x is actually not free variable from the viewpoint of the whole lambda abstraction. So it is defined as free variables of expression E minus this variable x. And the last case is this lambda application, free variable E1, E2. It's a simple case. You just apply the same function, this free variable function, individual expression, and then add them up. So this is the definition of the function that calculates the set of free variables. So here are a few examples. what is the set of free variables in expression lambda x dot x? It's perhaps an empty set because there is no free variable. And what about free variable of xy? In this case, there is no lambda binder, so both variables x and y are free variables. What about free variable of lambda y, lambda x, xy? In this case, this variable x is going to be bound here, and this variable y is bound here. So we find no bound variables, no free variables. The last case is lambda x, xy, lambda x, xy applied to lambda x, xz. So this is a bound, but this variable y has no corresponding lambda binder, and this variable z has no corresponding lambda binder. So you first apply the third case in this recursive function, and then apply the second case, and eventually you will obtain the set of y and z. So these are examples of calculating the set of free variables. So if you have the background from C programming language, you can think of free variables as global variables. So for instance, suppose that you have a C function foo, and you have some reference to variable x here. And this variable x is either global or local. If it is a local variable, it is declared here or it is given as an argument. So you can think of free variables as basically the counterpart of global variables in the C programming language. They are not bound anywhere. In the case of C programming language, these global variables are not declared in any function. But that's the notion of free variables. Now, what is the notion of closed? We say that an expression is closed if it has no free variable. In the case of a C programming language, if you have a C program that contains no global variable, then you can say it is closed. And similarly, in the case of lambda calculus, if you have no free variables, then we say that the expression is closed. Now let's make the first attempt to define the substitution. So our final goal is to define this operation E substituted for variable x in some expression. Because this expression is defined inductively, let's also try to define this substitution inductively. So we have three cases. Expressions are variable, lambda abstraction, and application. Let's first deal with the easy case. The first case, expression E for x. This expression is a variable, but this variable happens to be identical to this variable. And the other case would be this variable is not equal to this variable x. So in this case where y is not equal to x. So you have the first case and the second case from this case variables. So according to the informal description of the substitution, you want to find this variable x inside this expression and then substitute this expression E. So you go to this expression and try to find variable x, and we have just found an instance. So you make a copy of this one and then replace it with expression e. So that's it. What about this case? You try to find an instance of variable x, but there's no variable x inside this expression because we make an assumption that y is not equal to x. So therefore, you can simply find no instance of variable x, so this substitution has no effect. So in this case, the result is y. Because the most challenging case is in this lambda abstraction, let's first talk about this lambda application. We'd like to apply this substitution to an abstraction E1, lambda abstraction, lambda application E1 applied to E2. And this case is easy because it's just a matter of recursively applying the substitution to individual expressions. So you apply expression E for x in expression E1, and again apply expression E for x in expression E2. So we have finished this case. And the only remaining case is this lambda abstraction. That is, the question now is, what happens if this expression is lambda abstraction? So the remaining question is, E for x, here we have some lambda abstraction. So this is the remaining case. And in order to correctly define this substitution operation in the last case, we needed to understand two key properties of variables. To be specific, actually bounded variables. We needed to understand the two properties of bounded variables. So let's see the first property. In the rest of the lecture, we will try to complete the last case, this case, in the definition of a substitution, because the first three cases are just almost trivial. This is the only remaining case, and we will try to complete the definition here. So the first property of these bounded variables is their names. The name of a particular bounded variable does not matter. So what that means is that you have some lambda abstraction here. And this is the name of bounded variable. In this particular example, the name of this bounded variable is x. So this is the name of this bounded variable. But if you think about this bounded variable is just a placeholder. It just refers to whatever expression will be given as an argument, that's all. So if you don't like this particular choice of bounded variable, say x, you may choose to rename it, because the particular choice of this name for this bounded variable does not matter. If you want, you may rename a given bounded variable. So here's an example. We have this identity function, lambda x dot x, and suppose that you don't like this particular choice of name for this bounded variable. You hate this variable name x. And that's not a problem at all, because intuitively, this expression refers to an identity function. So you may choose to rename this bounded variable to y, in which case you obtain a seemingly different lambda abstraction, but essentially equivalent. These two guys are equivalent because both expressions denote identity function. And this makes sense because of the first property of bounded variables. The name of this particular bounded variable, it doesn't matter. And as a result, if you want, you may rename it. Later, we will see how to rename these bounded variables because we have to also take a care. We have to be very careful when we rename these bounded variables in order not to destroy the intended meaning of the given expression. But for now, let's just assume that we can easily rename bounded variables if we don't like this particular name. So now, how can we fill this case by exploiting the first property of these bounded variables? The name of bounded variables does not matter. We may rename these bounded variables. So we can give the so now suppose that we have this case. If so we are now going to deal with this case where the expression in this position is a certain form of lambda abstraction. So from the first property of these bounded variables, if we have something like this one, where this variable x is equal to this bounded variable in this position. In this case, we can ignore the substitution. So that is, the result is lambda x a. So why is it that? Well, intuitively, we may choose to rename the bounded variable x into something completely unrelated to variable x. So for example, something like lambda z dot d prime. Inside this expression, there is no variable x. Then it's pretty easy to see this has no effect because this variable x has disappeared inside this expression completely. Inside the expression E, here, you may find some variable x. But inside the expression E prime here, x has disappeared because we renamed this x into a different variable z. Then this substitution is going to have no effect because you can find x nowhere. As a result, we have this equation. If this lambda abstraction has the same bounded variable as the variable in this position, then it has no effect. The substitution has no effect. All right. So let's formally define this notion of renaming bounded variables. So we learned that the first property of a bounded variable says you may rename bounded variables because the name of bounded variables doesn't matter. So let's define this notion called renaming. So formally, we introduce new judgment written E equivalent alpha expression E prime. And this equivalence means that you can rename bounded variables in expression E to obtain E prime and vice versa. So what that means is that you rename bounded variables inside expression E and obtain expression E prime. Or you can start from this expression E prime and rename bounded variables expression in the expression E prime and then obtain expression E. So if we can think of this operation as a conversion, like converting expression E into expression E prime by renaming bounded variables, we obtain something called alpha conversion. And this equivalence relation is called alpha equivalence relation. It's a specific example of equivalence relation between expressions in lambda calculus, but by historical accident, it is called the alpha equivalence relation. And you can also say that we apply alpha conversion to convert expression E to E prime, or from E prime to expression E. So here are a few examples. Lambda x dot x, lambda y dot y. Perhaps these two expressions are related under alpha equivalence relation, because here, if you choose to rename this bounded variable x to y, you have to convert this one to y as well, because this variable x refers to this bounded variable, which complies with our intuition that these two expressions are indistinguishable except for their choices of this bounded variable. These two expressions are just equivalent. The next example is lambda x, lambda y, xy. This time, I'm going to leave this variable y intact, but I'm going to rename this boundary variable x into z. So this is renamed to z, but I'm not going to touch this variable y. So we have lambda y, and this x should be renamed to z because we are going to rename this one to z. So this is z, and this one remains the same. So we also have this alpha equivalence relation. And similarly, in the next example, we are going to rename this variable y and leave this guy as it is. So this guy x stays the same, but y is renamed to z. Then x is renamed to itself. Sorry, we don't rename it and rename this variable y to z. So this is another example. Finally, we can actually rename these two variables simultaneously. And moreover, we are going to rename this bounded variable x to y and this bounded variable y to x. In other words, we are going to swap variable x and variable y. And what's the result? This one is renamed to y, so lambda y. And this one is renamed to x, lambda x. And x has been renamed to y has been renamed to x. This case is interesting because we do not introduce any new variables, unlike these two cases where you introduce new variable z. But in this case, we do not introduce any new variable. We simply swap the existing two variables, x and y. And it turns out that these two expressions are related under alpha equivalence relation, which makes sense because both expressions, this one and this one, denote the same function given me the first argument, given me the second argument, and then I'm going to apply the first one to the second one. And this one also says, given me the first one, given me the second one, I'm going to apply the first one to the second one. So despite their syntactic differences, these two expressions denote essentially the same function. So they are related under this alpha equivalence relation. So later, we will give a formal definition of this alpha equivalence. But for now, it suffices to remember that by renaming bounded variables, you can convert it into another equivalent expression. And this equivalence relation is called alpha equivalence. And this property, this equivalence relation is introduced because we have the first property. The first property is you can rename bounded variables without changing the meaning of a given expression. So back to the definition of substitution. These cases are gone, and we have finished the first part in the last case. So the last case is expression e prime for x, and here we have some lambda abstraction. The first is lambda x dot e, and in this case, this substitution has no effect because we have the same bounded variable as this variable x. And why does it make sense? This is just lambda x dot e, because you can temporarily rename this bounded variable x into something completely different, lambda z dot e, for example. Then obviously this substitution has no effect. So this is the result. So you ignore this one, and then you convert it back to original lambda abstraction. So that's the first case. So if you generalize this observation, you have something like this one. If you have expression e prime for x and expression e, where x is not in free variable of expression e. So in other words, this variable x is not a free variable in the expression e, then this substitution has no effect, which makes sense intuitively. This substitution, you can think of this substitution as trying to find a global variable in expression e, and then substitute e prime. But if x is not in the set of free variables of expression e, there's no such global variable in expression e. So therefore, it has no effect. And you can think of this case as a special case of this one, because this lambda abstraction, it's a set of free variables, does not contain this variable x. So this so we have looked at the first property of bounded variables, which is you may choose to rename bounded variables to something else. And what about the second property? The second property of bounded variables is a free variable. Let's say we have expression e prime for x e. If you have some free variable in expression e prime, then in the resultant expression, it stays still free. So let's just say there's some variable z here, and it's a free variable. So g is in the set of free variables of the expression e prime. Then after applying this substitution, z is still free variable in this expression. That's the second property. To better understand the second property, let's try to complete the definition of a substitution in the last case. So let's consider this case. E prime for x in lambda abstraction y dot e. For now, let's start with some wrong definition where So where x is not equal to y. If x is equal to y, if these two variables are equal, then we go back to the previous case. We go back to this case. If these two variables are equal, then this substitution has no effect. Now, so we assume that x is not equal to y. Let's say that we erroneously write the resultant expression this way, E prime for x in expression E. And the problem here is if variable y is in the set of free variable of expression E, something bad happens. So previously, in this case, variable y is free. But here, variable y suddenly becomes bounded variable because it has a corresponding lambda binder. So with the addition of this assumption, y is in the set of free variables of expression E prime, something bad happens here. This variable y, which is supposed to remain free, suddenly becomes a bound. So here's an example. Let's say lambda x, lambda lambda y dot x. This is applied to variable y. And by the definition of this beta reduction, we can rewrite it as y for x in expression lambda y dot x. So this is okay. Then, according to this wrong definition, what happens? We propagate this substitution into the body of this lambda abstraction. So you have lambda y dot y for x, x. And this is y. So this is lambda y dot y. So this variable y, which is previously 3, suddenly becomes a bound, which is not acceptable because the second property of these bounded variables and free variables is a free variable should stay free even after this substitution. Any free variable inside the expression E prime should remain free. But in this example, this variable y is free, but after substitution, it becomes a bound, which doesn't make sense. Why is it that this conversion doesn't make sense? The reason is, if we think about this inner lambda abstraction, this lambda abstraction simply ignores the argument y. It just takes the previous variable x. Y is just ignored because it never appears here. So, intuitively, this expression should be equivalent to lambda x dot lambda z dot x y. Because we are going to ignore this one anyway. So it's okay to rename it to something completely different. Lambda z dot x. So now everybody understands these two expressions are equivalent because this variable is not used at all. Now let's apply substitution. This one becomes y for x inside lambda z dot x, which is lambda z dot y for x, x which is lambda z dot y. So in this case, this variable y remains free. This is free, so it stays free. But under this erroneous, wrong definition of substitution, this variable y suddenly becomes bound. So this is wrong. So what this example suggests is we require that y should not be free variable. If we are going to propagate this one into inside this lambda abstraction, then we have to make sure that y is not free variable in expression E prime. So that's the second part in the last case of substitution. So let me summarize it again. Currently, we are looking at this problem, E prime x, where this one is lambda abstraction. So the first case is E prime x, where lambda x dot E. This bounded variable x happens to be identical to this variable x. In this case, thanks to the first property of bounded variables, that is, we may rename bounded variables, this one into something completely unrelated like a z, then this one has no effect. So in this case, we may simply ignore this substitution. And the second case is, this is now different variable. So we have x is not equal to y. And we'd like to propagate the substitution into inside this lambda abstraction, E prime x e. But this is permitted only if y is not found in the set of free variables. So this is the additional requirement. So we have dealt with the two cases. And let's go back to this example. So in this wrong example, what happens is that this variable y, which was in the beginning, it is free, but suddenly it is bound. And this phenomenon is called capture. So figuratively, this variable y was free, but now it was captured, and it is now bound. It's no longer free, no longer free. So this phenomenon is called variable capture, or variable capture. Variable capture. So in order to avoid this bad phenomenon, or in order to avoid this bad variable capture, we require that this variable y is not free variable in the expression E prime. So in this way, we avoid this phenomenon called capture. So this substitution is called capture avoiding substitution. It simply says that a substitution that is well defined, so that captures are always avoided. If you fail to avoid the captures, something bad happens like this one. So you always have to make sure that y is not free variable in the set free variable of expression E prime. Now, what happens if the last case is E prime for x lambda y dot E? But what happens if x is not equal to y? That's good. But y is in the set of free variable of expression E prime. In that case, you certainly don't want to move this substitution inside this lambda body, because as we have seen in the previous example, it's precisely when captures occur. So you don't want to propagate this substitution. Then what choices are we left with? We have to rename this variable y to something else, something new. so that we can propagate this one into this lambda body. So the plan now is we are going to rename this bounded variable y to something new. Let's just say variable z. So the plan is we are going to rename this bounded variable y to new variable z, and then move the substitution inside the lambda, the body of this lambda section. Then what are the requirements on this variable z? First of all, we'd like to choose variable z that is not equal to, of course, y. If z is equal to y, this operation is no operation. So z should not be equal to y. And second, z should not be in the set of free variables of e prime. If this requirement is not met, then we might see variable capture. So go back to the second case. Here we require that this variable y is not in the set of pre-variables of expression e prime. Similarly, so we are going to have something like this one, e prime x, blah, 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 blah. So in order to avoid the capture, this variable z should satisfy a similar requirement written here. So z should not be definitely in the set of pre-variables of expression e prime. And finally, we have this requirement. What is the relation between variable z and variable x? We compared the variable z and y, and of course we don't want variable z is equal to x, because if this was a variable x, something bad, this basically doesn't make sense. So in order to obtain really fresh variable, we require that z should be different from y, first of all, and z should be different from x. Then z is going to be really fresh variable. So now we have chosen a fresh variable z, and there is one more condition that we have to consider, which is even if z is not equal to y and z is not equal to x, you cannot z to be some free variable inside expression e prime. If that's the case, we are going to see another instance of capture, because if z is free variable in expression e prime, then you might see some variable z inside expression e prime. So inside expression e prime, you might have z, and then there's some chance that z becomes bound after substitution, which is not acceptable. Remember that the second property of this substitution is if a variable is free in expression e prime, it should remain free here. So in order to make sure that this capture does not occur, you have to make sure that z is really fresh by satisfying this requirement. Z should not be found as a free variable inside expression E. If you fail to meet this requirement, there's a slight chance that this expression E prime produces variable Z, which suddenly becomes bound when it is supposed to remain free. So we have these 6 conditions. These 4 conditions deal with the variable Z, and it makes sure that the variable g is really fresh, and moreover, it never introduces variable captures. So if you have these 6 conditions, side conditions, then you may rename this bounded variable y to z, and then move the substitution into the lambda body. So the last case is something like this one, e prime x lambda y dot e, where x is not equal to y, and y is not, y is in the set of free variables of e prime. So you have to choose some new bounded variable. You have to rename this bounded variable because of this condition. And we are going to rename this bounded variable y to z, so that we can move this substitution into the body of this lambda abstraction. And in order to make sure that z is really fresh, we need these 4 conditions. G should be different from y, of course, and G should be different from x. And in order to avoid the capture, G should not be in the set of free variables expression E prime. And G should not be in the set of free variables of expression E. So I guess I think I needed to further elaborate on this condition. So if this condition fails, what happens? Let's say G is in the set of free variables of expression E. Then it really doesn't make sense. It's something like this one. You have lambda y dot z, and I'm going to rename it into lambda z dot z. In this example, in this expression, this variable y is ignored, but suddenly this one becomes an identity function. So in order to prevent such an abnormal case, we require this condition. And finally, the last question is, what is the expression here? So remember that our plan is we find that because of this condition, y is in the set of free variables expression E prime. Y is already found in expression E prime. So you have to rename this y into something new. Okay. So we are going to rename y to z. So this is really fresh. And in order to ensure that variable z is really fresh, we make sure that these 4 conditions are met. Now z is really fresh. So we move this one inside the body of lambda abstraction. And what is the expression here? It turns out that because we have chosen variable y, which is really fresh, we just swap these 2 variables, y and z. So we introduce new operation, y, bidirectional arrow z, and expression e. And this operation literally swaps variable y and z. So here is an example. X swap y in expression lambda x, lambda y, xy. This operation is actually easy to apply because you just don't care whether it is free or bound. Whenever you find any instance of a variable x, you simply swap it with y. And conversely, whenever you find an instance of variable y, you simply rewrite it as variable x. So this one becomes y, this one becomes lambda x, this one becomes y, this one becomes x. And it turns out that you'd like to swap variable y and z in expression E. So this is the last part. And the intuition behind why this makes sense is by swapping this variable y and z, you do not change the meaning of a lambda abstraction, but only change the choice of your name of this bounded variable without changing the meaning at all. So it turns out that this is safe. So this is the last case. So as we have seen in this formulation of substitution, the definition of a substitution is a lot trickier than we originally thought. So let's go over all subcases. So this is the first case this is the first part when the expression here in this position is a lambda abstraction with the same bounded variable. And this is the second case, this is the second case where in order to avoid the capture, we require this new condition. So this is the first case. The first case in the last part, and this is the second case, and this is the third case. And the third case is written over here. So it looks quite complicated, but essentially what we are applying here is the two properties of bounded variables. The first is, if you want, you may rename bounded variables to something new. And the second property is, a free variable should remain free after substitution. So we have these three subcases when the expression here is a lambda abstraction. And remember that in the third case, we have this sixth extra condition. And here we introduce this swapping operation. And to formally prove that this operation makes sense, we have to actually go back to the alpha equivalence. So let's define the alpha equivalence. Expression E is alpha equivalent to the expression E prime. It means that you rename bounded variables in expression E and convert it to expression E prime, or the other way around. For example, you can rename bounded variables in expression E prime to obtain expression E. So the last step is to give inference rules for this alpha equivalence. So first, we have three cases: variable, lambda abstraction, and application. So what about the first case? This variable x is alpha equivalent to x itself. This is a free variable, so there's nothing you can do about this variable with the renaming, simply because there's no bounded variable. So x is alpha equivalent to itself. And what about the easy case, this one, expression E1, E2? This is alpha equivalent to expression E1 prime, E2 prime, if their individual components are alpha equivalent, E2 alpha equivalent, E2 prime. The last case is this lambda abstraction. First, lambda abstraction, we have lambda abstraction. But what happens if the lambda abstraction here happens to have the same bounded variable x? In this case, it suffices to show that these two expressions are alpha equivalent. And finally, x.e And then we'd like to compare this lambda abstraction against the lambda y dot something. And in this case, we assume that x is